Dear friends, today we are discussing about the determine the position of centroid of standard sections in which channel section or Z section, and we are also going to see the unsymmetrical I section. In the previous session we learned about the determine the position of centroid of standard sections, T section, L section or angle section, and I section. I section which is only symmetric via T. And we also made some conclusions that by solving the equal angle sections and unequal angle sections of the L section portion, in which we stated that for equal angles the centroid about the x-axis is equal to the centroid about the y-axis, whereas in the case of unequal angles it will not be the same. And it is also observed that the centroid for the L sections are angle sections. It is outside of the given shape. That means if this is our L section, the centroid location is somewhere here. The location of the centroid is somewhere here. That means it is not in this portion, not in this vertical leg portion, not in the horizontal leg portion, but it is outside of the given shape. So it is to be remember that the centroid is outside of the shape of the angle or L sections. If we made it, we can also brought to the within the section by varying its dimensions, but it is the standard statement that generally it is outside of the shape. Now, so these are the angle sections. So for these angle sections, to understand the dimensions, because these dimensions are available in the IS code book of the standard sections, in which while you are taking the dimensions, it should be noted that the A is vertical leg dimension and B is horizontal leg dimension. A is a vertical dimension and B is a horizontal dimension. This should be keep in your mind while solving the problems. So this is the example of the equal angle section and unequal angle sections, right? Today in this session, we are going to learn about the determine the position of centroid of standard sections, that is channel section or Z section and unsymmetrical I sections. First we see the unsymmetrical I section and thereon we will move to the channel or Z sections. Now unsymmetrical I sections, to determine the centroid of I section with the following data. We already covered the procedure how to solve these type of problems. Hence, we are directly giving the problem statement. Determine the centroid of I section with the following data. So, an I section is containing a top flange, bottom flange, and web portion. So, this is the top flange, this is the bottom flange, and this portion is the web. The flange of the top is given 100 mm by 10 mm, hence this is 100 mm, and by 10 mm. The bottom flange is given 80 mm by 20 mm, hence this is the bottom flange. So this is 80 mm by this height is 20 mm, and web 20 mm by 150 mm. 20 mm is the thickness of the web and 150 mm is the height in between the flanges. So after drawing this sketch of the figure with the given dimension and try to inspect is there any symmetry axis is there or not. If you understood that here the y axis that is parallel to y axis makes some symmetric position. So this is the symmetric position axis. So it is symmetry about the y axis. So after inspection, I understood that it is symmetric about the x axis, right? So this statement is wrong. Only it is symmetrical about the x axis. Hence it is symmetry about the y axis, which is given here. This is symmetry about the y axis. Hence, x bar is equal to LD by 2. So that we can directly calculate the x bar without using the analytical method. So you can also see that the portion of the top flange is equal in two parts about this parallel to y axis, and bottom flange is also symmetric about the parallel to y axis, and web is also parallel to y axis. Hence we are stated that symmetry about the y axis, therefore x bar is equal to LD by 2. Then what about the y bar? So in order to y bar we need to draw a line to identify the symmetry. Is it is symmetry, the top flange is not equal to the bottom flange. Hence, it is not symmetry about the x-axis. Therefore, you need to calculate the y bar by analytical method. So, we need to pose the entire shape into the first quadrant. You please see that. Please notice here, we are not mapped this bottom flange with respect to the origin, because the extreme left dimension is for the top flange. Hence, we are kept the distance of the bottom flange from the origin, so that the top flange, which is the leftmost portion of the top flange, should match with the y-axis. So this is the maintaining the position of the entire object in the first quadrant. This precaution you should be taken care. So this is the precaution you need to take care while uh, while approaching the position of the shape in the first quadrant, right? So observe these two portions. One side it is attaching and other the bottom flange is somewhere distance, because to maintain the alignment with respect to the y-axis, and the entire object should be placed in the first quadrant. Right? So the procedure to solve: using the analytical method, just simply use the first moment area method. So tabulate the distances, areas in the as shown in the table. The bottom flange area is 80 by 20. So this is the 80 and this is the 20. The same has been mentioned here. And 1600 is the value. Similarly, it's we are intended for the y-axis. So we will come to these calculations later. First you see the areas for the web. This is 150 is the distance between the two flanges, that is nothing but height of the web, and thickness is 20, therefore 150 by 20, that is 3000. And similarly for the top flange, 100 is the width and thickness is 10. So multiply that you will get. Then add these all the three areas, then you got the 5600. Now calculation of y of the individual object, that is for the bottom flange, we need to calculate the y values from this origin, always calculate from this origin. Hence this is the y bar for the y1, this is the distance of y1, therefore y1 is 20 by 2, y1 is 20 by 2. Similarly for the web portion, from this point to, we need to take the midway of the web portion, midway. So up to mid portion, let us say up to this one, this is the distance. So this distance is 20, this is the 20 plus 150 by 2, therefore you got the 95. Similarly for the top flange, we need the y3 calculation from this point to this point. So that is the half of the top flange. Therefore, from this point, it is 20 plus 150 plus 10 by 2. Therefore, 20 plus 150 plus 10 by 2, 175. After obtaining these values, just multiply with the area and y, you got the ay values. Then let's summarize those values and you will get the ay value. Then substitute in this equation ay value and area, you got the 85 mm. So we are already understood that it is symmetry about the parallel to y-axis, hence x bar is equal to LD by 2. The greatest distance in the x dimension is out of the 80 and 100, 100 is the largest dimension, therefore 100 by 2 is the 50 mm. So 50 mm is the x bar and y bar is 85 mm. Hence, your centroid will be 50, 85. So that is the showing of the centroid. So this is a asymmetric about one axis. The I section is asymmetric about one axis that we are seeing this one, right? Now we will try to asymmetric about the both the axis. The problem how it will looks like. See this problem. Determine the centroid of I section with the following data. Top flange 100 mm by 10 mm, 100 mm by 10 mm, and bottom flange 80 mm by 20 mm. See this, the same dimensions we are kept, 80 by 20, 100 by 10. The same dimensions we are kept, but web is also same 20 by 150, but the top flange, this sentence is important to identify the problem, either it is asymmetric or symmetric. So the top flange extended 30 mm beyond the right side of the web. So this top flange is not placed uniformly throughout the web. It is placed asymmetrically. That means he is saying that it is extended 30 mm beyond the right side of the web. So if this is the right side of the web, this is the right side of the web, then it is the top flange is extended only 30 mm, right? So this is the portion he has given, and we know that this is 100 mm. Therefore 100 minus 30 we have the 70, and the thickness is 20 of the web, therefore 70 minus 20, so this is the 50 from this point to this point. So this point to this point is 50. Now you please understood that it is 50 here and here it is 30. That means both are different. Both are different. So this is the main cause of your asymmetry. So due to this, what happens is it is not symmetric about the y-axis. If I try to bring it out as a parallel to y-axis line, is it symmetric? No, it is not symmetric because this length is not equal to this length. Hence, it is not symmetric about the y-axis. Right? If I am trying to get the, is there any symmetric axis about the x-axis also? No, because this portion is 100, this portion is 80, and it is not symmetrically laid also. Hence, this is not also be symmetric. Hence, both axes are unsymmetric. Hence, it is a asymmetric figure of the both the axes. So the next procedure is I need to locate the entire object into the first quadrant, right? Such that the extreme left and bottommost are to the axis. So this is the position I need to be place the figure, right? So you please better understood that here the distances, right? So this is the portion which is going to be touched, not this bottom flange is not going to be touched because this is 50, right? Now after labeling all the dimensions and unknown distances, like here I mentioned here, this what is the this distance, so this distance I am getting from this 50. So this is the 50, and you know that this is 80. Therefore 80 minus 20, so you got 60. Therefore 60 by 2, and so this is 30, and here also 30. Now this will become 80. 80 means 30 plus 30, 60 plus this 20. So this portion 20, total 80. So hence this is 30 and this portion is 50. Then what is this distance? 30 minus, sorry, 50 minus 30, you got the 20. So this is the way to calculate the unknown uh, values of the dimensions. So after getting these dimensions, then we will go for the analytical method of solving for the both the axes because it is asymmetric. Now you see this simple way of the same procedure we need to follow. Let uh, evaluate all the areas. Bottom flange 80 by 20, 80 by this 20, thickness is 20. So you got the area and web is thickness is 20 and height is 150, the same, and top flange is same 100 by 10. Here it is the thickness of 10. So we done the same thing. For the x-axis, x1, x2, x3, we need to calculate the individual centroids of the each figure. Bottom flange here, so this is the bottom flange. So for the x bar, it will be located somewhere here. Like in generally what we write 80 by 2. Generally what we write 80 by 2. But it is this starting portion of the bottom flange is not aligned with respect to the origin. It is not aligned with respect to the origin. So we need to add that extra distance 20. So we are need to add this extra 20 to the x values. So we are added this one. Therefore 20 plus 80 by 2. So similarly for the web portion also, for the web portion it will be 50. So 50 plus, because this distance is 50. This distance is 50. This is the 50. Hence 50. So from this point to up to web portion it is 50 plus 20 by 2, 60. Therefore you got the x bar value for the web, and top flange 100 by 2, because this total flange width is 100 which is aligned with respect to the axis only, hence directly you can take the half of the distance, right? So in this way we are calculated the x1, x2, y3, and the similar procedure adapted to calculate the y1 with respect to the y-axis, with respect to the y-axis. So we are doing calculations like this. So this is the y1. Y1 is 20 by 2. That means the thickness is 20. We required only half, that is the y1. For the web portion, total is 150. From this point to this point it is 150, and 150 by 2 being it is a rectangle, 150 by 2, and it is not started with respect to the origin. There is a distance of 20 is the distance between the web and origin point, hence we need to add this 20. So adding these values and you will get the y2, similarly y3. So calculate all these values and obtain the product of ax and ay, that is the first moment of area, and total summation of the areas for use to calculate in the centroid. Then apply the formula of x bar is equal to cx is equal to qx by a. So the values which are getting in the table, substitute all those values. Qx means ax and qy means ay. Then you got the x bar is 58.21 and y bar is 85 mm. Remember, this value of 85 mm is same as in the earlier case also, where in the first problem. So 85, you can see here also 85. You please note that this is the symmetric about the y-axis, where we got 85 for the y bar, right? And similarly, in this case also you got the y bar as 85, where this portion we are changed also, but you got the y bar value. So this is the our observation. If the areas are not differently oriented with respect to the y bar, with respect to the x-axis, either they are placed at the same level, then its centroid is not going to be changed, right? So this is the one of the conclusion by understanding the differences. Now we are moving towards the channel section. So in this channel section we are taking a ISLC 250 with the following data. The top flange 100 mm by 11 mm and bottom flange 100 mm by 11 mm. That means both the top flange and bottom flange are same. Web 228 mm by 6 mm. Now how it looks like? So this is the dimensions, right? So this is the bottom is 100 by 11 and top is also 100 by 11, and the web portion is 228 by 6 mm. I simply just taken the values of the rounded values from the tables of ISLC in order to easy to calculate. Right? So now the step is, after drawing the sketch, you need to identify the symmetry axis is there any. I could not get any symmetrical axis parallel to y axis. Is it symmetry about this axis? No. So is it symmetry? Can I say this is the symmetry line? No, because this portion, this half portion is not equal to this right hand portion. Hence this is not the symmetry. So now I am trying to get the symmetry axis about parallel to the x-axis. Now it is symmetry about this axis. You can see here. So this is symmetry about the parallel to x-axis. Hence we can directly write the y bar. So if it is symmetry about the x-axis, you can get the y bar value without using the analytical method, hence largest dimension by 2. So what is the largest dimension in the y direction? From this point to this point. This point to this point is given in the problem itself. It is 250 because channel section is represented with respect to its depth and weight. Now 250 is the total depth. Therefore, I can say that simply the y bar is 250 by 2. That means it is 125 mm simply. So this is the way to finding the symmetrical axes. So it is, and it also gives the easy solution. They can be asked in objective questions as in ESET also. Hence, remember these procedures. Now, after getting the symmetry, then place the entire object into the first quadrant to determine the x bar position, being it is not symmetry about the y axis. So it is only symmetric about the parallel to x axis. Right? Now the simple procedure, follow the same manner. So we need to calculate the x bar only. Hence you take the x1, x2, x3 values and areas, then multiply, you get the ax, that is nothing but qx, with the your figure dimensions. The procedure will be the same. So for the bottom flange 100 into 11, web 6 into 228, top flange 100 into 11. So multiply, you will get the areas. And for the x1, x2, x3, so x1, x2, x3. So this is the x1 value. From this point to this point is the x1. Therefore x1 is equal to 100 by 2. And similarly x2, x2 will be from half of the this web. So therefore 6 by 2. And top flange, it is also the same as the bottom flange with respect to x origin. Therefore the both will be the same. Then multiply, you will get the values of ax, that is nothing but qx. So by summation, solve for the x bar value. So it is given around 31.98 mm, and y bar we are already calculated, it is 125 mm because of it is symmetry about the parallel to x axis. Now represent the same thing in the final output. So this is the thing. Now you observe that in the channel section also, the location of the centroid is outside of the shape of the object. So this the same thing is happened in the angular sections also. Now the same thing is here also. Hence it is understood that for the angular sections and channel sections, the centroid is out of the given shape and it lies about the one of the symmetrical axis if it is the symmetry. Now we are moving to the another variation of the channel section. Now I would like to make it is asymmetric, so that it is also clear how to calculate the centroid for the asymmetric channel sections. For this, the top flange dimension and bottom flange dimensions are different. In the earlier case, the top flange is 100 by 10 and bottom flange is also 100 by 10. But this case, this is 70 by 15 mm. The thickness is also varied, right? And the width is 100. Now the width is 70. So now you can see that here the same thing. 100 is the top, therefore this dimension is higher, and at the bottom bottom flange it is 70, hence this is the 70, right? So this is the uh, asymmetric about the even x-axis also, parallel to the x-axis also it is asymmetric. So now the figure has to be drawn with the dimensions. So this is the figure we are drawn with the dimensions of the given dimensions like 225, 8, and for the bottom flange 70 by 15. This is the 70 by 15, the shape has been drawn, and due to that we are also understood that how to place the entire figure in the first coordinate. So we placed the object into the first coordinate. Then the same procedure, because it is asymmetric about the both the axes, there is no symmetrical axis available along the x-axis and y-axis. So calculate the x1, x2, x3 and y1, y2, y3 and obtain the ax and ay products, that is qx and qy. So using these dimensions, now we are going to calculate the ax and ay products. Follow the same instructions. Always see where it is the origin. So calculate everything from the origin. So this is the point of origin. So keeping in mind that while calculating the x1, x2, x3 values and y1, y2, y3 values, always take the dimensions from the origin only. So therefore bottom flange 70 by 2 for the x-axis, as it is 70, hence it is 70 by 2, and for the web it is 8, therefore 8 by 2, top flange is 100 by 2, right? Whereas for the y-axis it is coming the reference from this point of view, hence we take the 15 by 2, that is the y1, and web we need to add 15 and take the off of the web height. So, so, after the same procedure happened for the top flange also, then multiply the x1 x values with respect to the corresponding areas of the shape, then summarize the values to get the product of ax value, that is qx. There similarly for the ay, then to get the qy value, then substitute in the our formula, which is x bar is equal to cx, that is equal to qx by a. Then substitute the values we are whatever obtained from the table, and from that we are obtained x bar is equal to 23.34 mm and y bar is equal to 137.07 mm. Then locate the centroid. So this is the way you need to locate the centroid with respect to the origin. Now we are moving towards the Z section. Z section, as in the English letter like the Z, we are not going to take the same value, same proportion. We are not going to deal this Z section. We are going to deal this shape of the Z section. For this type of jet sections, we need experimental procedure. We need experimental procedure, not the analytical method. But for this type of shapes, analytical method is suitable. So please note that normal alphabetical Z cannot be determined by the analytical method. If you are attempted to do the same thing, it takes more time to calculate the accuracy levels, but it is easily be solved by making it the slant jet portion into the vertical jet portion by analytical method procedure is easy to solve, right? So we will take the vertical jet type of sections. There is no slant portions in the jet alphabetical, so we are considering for the easy calculations. This is the data is given. Top flange is 150 mm by 20 mm. That means this is the top flange 150 by 20 mm, and bottom flange, this is the bottom flange, right? And web is this one. So this is the web. So using this all dimensions, we are going to the calculating the centroid position of jet section. For that, we need to draw the sketch. So this is the sketch we are drawn with the given dimension 150 by 20, that is the top flange, and bottom flange is also 150 by 20. Web is 200 by 50. The same has been drawn and inspected for the symmetry. Can you find any symmetrical axis here? Let us try to draw symmetry axis. Is it symmetry or not? We have to see that. So I am drawing a line here to understood that whether it is symmetry about the both the axis. No, because it is not the mirror image. If it is a mirror image, it should be come here, right? But it is not this side, so it is on right side, so hence it is not the symmetry about the x-axis. Now I am drawing about the y-axis parallel to y-axis. Is it symmetry? No. By seeing itself we can say that it is not symmetry about the, it is not symmetry because this with respect to this y-axis, this portion is this side, right? So it is not symmetry. Hence we are try to uh, adapt the procedure of asymmetric sections using the first quadrant positioning. So I place the entire object into the first quadrant such that the origin is completely on the positive side. So we made it is a total coordinates are into the positive side. You please also see that here this portion is away from the origin and this portion is touches to the origin lines. So that the entire object is in the first quadrant. So after understanding, in order to make it into the first quadrant, so this is the distance of the bottom flange away from the origin, right? So you will see that also. See, so this is the distance, this is the distance 135. So this is the distance of 135. Simply we are subtracted 15 from the 150. This is 150 and this is the 15, so that you will obtain the distance. So the same has been mentioned here 135, right? So using the figure, I calculated all the values in the similar procedure what we explained in earlier procedure of the finding the channel sections and I sections. The same procedure is here also be followed, and we got the values of summation of the all the areas and product of a and x values and product of a and y values with the similar procedure by taking the values of x1, x2, x3 and y1, y2, y3 values from the origin O. Now locate the centroid with the obtained values, that is x bar is equal to cx is equal to qx by a, and for the y bar also cy is equal to qy by a. So substitute all these values and locate the centroid. So this is the centroid location. So everything is from the origin, right? This 142.5 is the x bar dimension. We know up to this point it is 135. Up to from this point to this point it is 135, and up to this point it is 150. Hence your centroid is lies in the section, on the section, right, of the web portion, right? Now the centroid is located in the web portion. Centroid position is within the web portion, right? So because it is less than 150, and this the 120 is the height, so this is the 120 distance, right? Now similar jet section has been given, but the reversed reversed can also be taken place. You see that now this is the orientation. You please compare the jet shape. Here this is the jet shape. Now they are wanted to the section should be like this. If this is the case, how you are going to the analyze the section? It is mirror image of the jet section. So so mirror image of jet section as shown in figure. So now the orientation of the jet has been changed. So according to this given dimension and orientation, the similar procedure is adopted to solve the z value of the centroid positions. So look at the, is there any symmetric axis are available? No, there is no symmetrical axis available. Hence it is asymmetric about the both the axes. So it is asymmetric. The procedure is simple. Then locate the total object into the first quadrant and solve for the centroid using the analytical method procedure. That means we obtain the x1, x2, x3 values and y1, y2, y3 values from the origin. So the distance here is also 135 because this distance is 150, this distance is 150, and the inner dimension is 135. This is the inner dimension 135. This is the outer dimension is 150 up to this point, and up to this point it is 135. So that is the difference, right? So we need to keep in that mind, calculate the values. So we are calculated the similar values, and please understood that we will surprise the values what they are producing. Even though we are changing the orientation, just the values of the top flange and bottom flange, you please remember these values. You please remember these values. For the top it is 75, sorry, it is for the bottom it is 75 and the top it is 210. So remember, for this orientation, what about the orientation of these values? They are reversed. This is 75, this is 210, right? Just reverse it for the orientations. So this is the thing you need to keep in your mind. So if you are changing the orientation, the values will also automatically changes, right? So top flange become the bottom flange values, but your centroid will be the same. You see that the centroid 142.5 and 120 mm, which are the both will be the same as you obtained in the earlier case also. So please note these values, keep these values in your mind, 142.5 comma 120. Now see the other orientation which are we are solved in earlier problem. So this is also the same, the both are same, 142.5 comma 120. That means without changing the dimensions of the shape, if the area has been positioned at the same levels, but the we are just shifted in at the same level from one point to another point, there is no variation in the centroid is happened, subjected to the same dimensions. So that is the conclusion we are obtained by taking the jet section as the mirror image. So the same thing has been explained for your better understand. It is understood from the questions 13 and 14 that the centroid position is same for the both the cases because of similar dimensions and area distribution at bottom and top is similar and distance is also same. So in this case we are obtaining the centroid is same. So it is requested to solve the problems which are mentioned here. So determine the centroid for the following figures by assuming the suitable dimensions as per the shape. So here you see that the jet shape, here it is bottom and top flange are not equal dimensions, right? Not equal dimensions. And similarly for the channel sections also, which has been general channel section will be like this. So we changed it into the this type of U shape. So in the U shape, the left flange, left web we can say, because verticals are known as web. So left web and right web. So this is also right web. So both are not equal. So due to this, it is not symmetric about the y-axis. So it is not symmetric. So this is not the symmetric. So is it symmetric? No. Is it symmetric? No. So hence it is the for the both the axis it is asymmetric. So solve these problems with the help of the analytical method to better practice. Today in this session we discussed about the determine the position of centroid of standard sections, that is unsymmetrical eye sections and channel sections and jet sections. We are also noticed that the centroid of channel section is outside of the shape, and similarly the jet section, it is located at the within the web portion, and it is also examined whether it is the same for the jet section of the different dimensions, so that to be practiced yourself and get the statement for the same. Thank you.